Good morning, class. Today we'll be talking about intrinsic spin. And as always, before going into the main portion of the lecture, I will give a brief review of what we did last time, and this will actually connect closely to what we'll be doing today. So last time we talked about angular momentum and the Zeeman effect in particular, and the effect of the change in the potential energy, and also kind of the force on the magnetic dipole due to the angular momentum of a charge moving in a circle or orbit around a nucleus. So let's consider that one more time. So we considered the Zeeman effect, the very last thing we did. And for this we considered a circulating charge in a magnetic field. And we looked at how this affects the system if the system has orbital angular momentum. In particular, we looked at its potential energy, which we found to be mu dot b, where mu we defined to be something called a magnetic dipole. So U, the potential energy, can be rewritten as minus Q over 2m naught times angular momentum dotted into magnetic field with L dot B, and that is equal to, if you simplify, minus Q over 2m naught B also Z. And that can be equal to minus Q over 2 m naught B h bar m, where m is equal to 0, plus or minus 1, plus or minus 2, and so on. Okay? And recall that the magnetic moment is the area times current, and it can be rewritten as Q over 2m naught times angular momentum for some circulating charge. That's what we did last time, and we'll try to connect the L with this thing called intrinsic spin, which we'll talk about now. Okay, so the idea is electrons are known to have spin, probably you've heard before, and the analogy people often make for electrons and their spin is that they behave like tiny magnets. And the question we'll ask yourselves today is, what is the origin of the spin? And we'll try to model the spin using some quantum mechanical treatment. classical picture one often uses to describe an electron spin is that it's much like a rotating ball of charge, so therefore the ball of charge is angular momentum, and it's charged, therefore it gives rise to some magnetic moment. And we'll find that this is not quite the case, but the analogy can go fairly far in describing its behavior. Well, just to say that this kind of rotating ball analogy isn't quite right at all, because it turns out that the spin property of electrons is an intrinsic property, and it's not something that is arising from the rotation of a charge or anything like that. As far as we know, the electron is a point particle, and it's intrinsic, much like an electron has charge and it has mass, and so it has a spin. Okay. So let's consider an example using this classical picture as an analogy to try to motivate the behavior of an electron's spin. So let's consider a solid sphere with mass m0 and charge q uniformly distributed on the surface of the sphere. So it's not distributed throughout the volume, it's just distributed at the surface. Consider an example. I'm attempting to draw a solid sphere. Radius r, and this sphere is rotating with angular frequency omega. And so we can write down the magnetic moment arising from this spinning sphere charge as q over 2m0 times L, where we can rewrite L as moment of inertia times omega, which is equal to, for a sphere, 2/5 m0 r squared omega. And just as an aside, this is moment of inertia for a sphere. Okay. Now what we can do is we can consider mu as the current times area, and if we do that, we can write the following expression: q over 3 r squared omega and that's equal to, doing some gymnastics here, algebraic gymnastics, this times 1, and I'll write 1 in a strange way, times, and that's equal to 5 over 6 q over m0 L for this charged sphere that is having charge only at the surface, but is having mass m0 as a solid sphere. Okay. Alright, so that's giving you the idea that the magnetic moment arises if you have a charged sphere. And if you attempt to approximate an electron in a charged sphere, it will be having some magnetic moment that's proportional to its angular momentum times the charge divided by its mass times some constant. Okay, so that is an analytical expression to try to describe how a spin might arise, or intrinsic spin might arise. Now let's consider an experiment called the Stern-Gerlach experiment. So the thing we can consider next is called the Stern-Gerlach experiment. And it's set up by considering solar atoms in their ground state. And these solar atoms have 47 electrons in one atom with 1 electron in the valence shell. And that's like saying 1 active electron. And there is a magnetic field pointing along the direction, but it's not uniform. Okay, and if we do that, if we consider this, we can draw a picture that describes the experiment. There's a source of particles, solar particles. And they're traveling along the axis through a magnetic field. This is a magnet here, the South Pole and a North Pole, and it has some non-uniform field along the z direction. Okay. And on the right side is a screen where one can image the solar atoms incidence on the screen. And you can imagine some distribution of solar atoms on the screen, which may look something like this, or potentially something else. So for this experiment, we can consider the magnetic moment of the solar atoms, and it turns out they're behaving something like this. There's some constant g out front, times another constant uv, which we'll define in a bit, or megaton, and times s. S will behave a lot like L, but we'll just define it and use it a bit to try to understand how it behaves in terms of the observation in the experiment, for starters. Okay. So in the experiment, what you have is a force acting on particles due to the field. Okay, and that force will be equal to the special derivative of the potential. We know that what that is for the magnetic moment and the magnetic field. So we can write F sub z is d dz minus mu dot b. And that is equal to g mu b over h bar, putting the constant on front, b dz s dot b. And that can be rewritten as g mu b over h bar sz dbz dz. Okay. And so with this information, one can study the experimental result, compare it to the formula, and get a sense of what, for instance, sz is. These are all constants. This you could find given the magnetic field. And this is something that is right now completely unknown, and we want to learn about how sz behaves and what sz is. So let's do it. Let's take two results and compare them. And now let's take basically a classical result, and then kind of what we expect if quantum mechanics is playing a role in this system. So classically, what we kind of expect is something looking like this. With distribution, kind of spread like that. Along the z direction, with say some maximum value for mu on one tail and the negative maximum value on the other tail. And the picture is something like this, where the magnetic moment can really take on any direction. That's kind of what you would expect to happen classically. Okay? And this bump is a distribution of mu values. Now, quantum mechanically, recall that mu is linked to the angular momentum for rotating charge or distribution of a circulating charge, and it has two distinct values. So one might expect to see the distribution looking something like this. One bump, one location, another bump, another location. And indeed, this is what people observe if they do that experiment. Not the classical behavior, but the quantum mechanical behavior. So let's explore this expression some more. And guess some behavior for eigenvalues, SC. Let's say that they behave a lot like LZ, which is a good guess to make starting out. So we have from before this expression. And what we can do is rewrite that in terms of the following: B times G over H bar times M H bar, the eigenvalues for SZ, times dB dz dz. And that's equal to UB GM dB dz dz of BZ, hard to say. And recall that the derivative with respect to z of BZ and mu b, the constants, well, mu b is a constant, but the derivative of BZ with respect to z is known. Okay. And just note that GM is plus or minus 1 for the experiment. This is something we get from the experiment. And therefore we could say for the electron, G is about 2. Therefore, M is plus or minus a half. Which means that the spins of S as opposed to SC is going to be a half. Okay? So we're making a lot of statements, and what we can do is compare what we just found from this experiment with something that's more familiar. This angular momentum where L is equal to 1. Recall you have something like this. Some angular momentum giving rise to mu pointing in one direction or the other direction. Quantum mechanically it could take on 3 values. That's a projection onto the z-axis. You see in experiments, you expect from theory to have a distribution of values. This isn't drawn really great, but one centered around 0, one centered around 1, one centered around -1. Well, this corresponds to eigenvalues 0. M equals 1 H bar, and M equals -1 times H bar. Okay, so that's the analogy with what we've done before in the previous class, and what we're saying is happening now for spins. Notice there are 2 bumps here as opposed to 3 bumps there. so some important observations, which I've said some things already, or alluded to them at least. So recall that we're making an analogy between angular momentum and this for electron moving around an atom with angular momentum, or for charge, ball of charge, or electron behaving like a ball of charge. We're attempting to describe that as the intrinsic spin of the electron, which isn't qualitatively correct or quantitatively correct, but it gives us some way to attempt to tackle the problem. And we're having this experiment to help us make this analogy, make this connection. And let's make some important observations. Which I'll add may be surprising or unfamiliar. So we have S is equal to 1/2. Okay, they're no longer integers. We've dealt with the whole class so far. Therefore S sub z takes on values h bar over 2 or minus h bar over 2. Absolute value for S is now half times f plus 1 times h bar. And we found already that G is 2 for the electron. Okay? And let's remark that this S spin, electron spin, is an intrinsic property not dependent on any internal structure. So there's not really a rotating ball of charge that comprises the electron. Okay, so that's what I'm claiming is the case, because we one for one we kind of claim half by considering the electron as the ball of charge. Another remark is that Schrodinger's equation, or the psi from Schrodinger's equation with parameters x and t, can't be used to describe spin states. So we'll need to consider something else to help us describe spin states, and that something else is some eigenfunction that is known as a spin eigenfunction, and that is another Greek letter which is called chi. So the total wave function we can that's not quite what I want to say. So when considering electron spins, what we need to do is, instead of using psi, we need to consider psi times chi. So there's a product of psi and chi that's needed to describe the wave function, including spin. And we can write h naught acting on psi is IH bar, kind of what we know from before. And the H prime, the spin-dependent part of the Hamiltonian, I'm claiming acts on psi to give you I H bar d pi t dt. And note that there is no x dependence. There's no position dependence. Okay. And this is a star asterisk, not a complex conjugate, of course. And let's now find some notation. We can write chi in terms of chi plus and chi minus, and in terms of the matrix operators or the matrix representation, chi plus becomes 1, 0, chi minus becomes 0, 1. And we often represent spins, intrinsic spin, to do matrices. And this is why we introduced the matrix notation earlier on, so we can talk about it here. Okay, so that's chi. We'll do chi plus and chi minus. Let's take a step back and look at this rotating ball charge picture again. And let's define some things we didn't define before, like Bohr magneton. And other constant we wrote down g, which is called g factor, which I didn't define before. So we call that mu is my moment for this rotating ball charge is 5/6 times q over m naught times angular momentum, and we wrote that in terms of a mu b before, and mu b is the Bohr magneton, and that's defined to be g times h bar over 2m naught. And we can write mu in terms of the Bohr magneton. And if we do that, we get the following. We get g times ub over h bar times L, where g is this constant I described before, but it has a name, and it's called the g factor. And it was 2 we found for the electron, But it turns out that this factor can change. It really depends on the particle that you're looking at. And also the kind of charge configuration. So an example is for an electron moving in an orbit. We call that mu is Q over 2 naught times L. And if we write this as the Bohr magneton, we find that G must be equal to 1 in this case. Okay? And it's a different value for the intrinsic spin of an electron. Now let's review what I said earlier about trying to draw an analogy between this angular momentum and this intrinsic spin, saying that they're behaving. Let's start by treating them the same. But I said that's not typically what you really should do. And what we'll do next is using that idea, making an analogy between L and S, this angular momentum, and the spin operator. But what I'll do is say that they behave the same. So I sort of did earlier in working on a problem. But let's make that a little bit more formal. And write falling. So if that's the case, then what you can do is write mu, the intrinsic spin, as mu E times G over H bar times S. Okay? And recall that from experiments, we got a value for G. And for the electron, G is 2. And actually, if you do very careful experiments, it's not quite 2, but it's very close to 2. This is interesting. It's this really long number that's not an integer by any means. And for the proton, turns out G is minus 5.6. Again, these are experimental values. And neutron is G plus 3.8. Note abandon, and B, note that angular momentum, rather the absolute value of the spin operator, is a half times half plus 1 times H bar, and S is equal to a half for the electron, which we talked a little bit about before, but it's good to say it again. let's take a look at the first and second in-class assignment. Return. Let's take a look at the Hamiltonian one more time and the eigenfunctions on the spin states. So note that the Hamiltonian for the spin particle in a field is given as follows. It's minus mu sub s dot d, where the sub s is for the spin as opposed to the angular momentum. So we have some charge, in this case, some spin particle with s, and in a field you can consider the v component being not z hat. So for an electron in particular, this Hamiltonian becomes g u b over h bar s dot b, which is equal to g u b h bar a naught s z, and g for the electron is 2, we found before. And the eigenfunctions for s z are these chi's. Behave like the following. SC acting on the operator, rather the operator acting on the eigenfunction gives you the eigenvalue times the eigenfunction. Well, these are subscripts at half for the spin for the electron times m sub s, or rather n m sub s, and over here the subscripts at half at m sub s are also written for the same eigenfunction. And m sub s takes on values plus or minus a half. This is what I'm stating, and we haven't really shown it. We can say that it's something that arises from the experiments that we do, and we're trying to describe the experiment. So the eigenfunctions in the matrix representation are very useful for calculations. So we'll consider them. Chi half is 1, 0. chi half minus 1 half is defined to be 0, 1. Let's take another example. For a proton, which also has a spin. Mu for the proton is G sub B over H bar S. Now it has the same form as the electron we did before, but G in this case is 5.6, and therefore the Hamiltonian is minus G proton, which means E over H bar E S Z. Okay. Now let's take a break from the lecture to take a look at the third in-class assignment. When we return, let's consider more analogies between what we've done before with angular momentum operator and essentially what we like to learn about the spin operator. Let's make another assumption. This is going to be a big assumption. That the following commutation relations work. This is something that you will do in greater detail later on in your quantum career, but for now we'll just take them as given. And these are the same ones we did before. Instead of having L, we replace them with S. So the commutation relation with X, Sx, and Sy is IH bar S sub Z. Okay? And then the others that followed from last time. We can also consider the matrix representation of the SE in some more detail, including not only the eigenvector representation, but also the representation of the operator. The eigenstates that are linked to the matrix SZ, recall, are this chi half, where the first index refers to the S, the second index refers to the M sub S, and we had also chi half minus a half. And let's define this chi half because it's tedious to write one half each time. So this chi plus, and this chi half minus 1/2, and it's chi minus. So it's plus for the plus a half and minus for the minus a half. Just to make notation a little bit less tedious. And chi plus is defined to be as 1, 0, and chi minus is defined to be this 0, 1 eigenvector. And they behave in the following way. S, Z, acting on chi plus gives you h bar over 2 chi plus SZ acting on chi minus gives you minus h bar over 2 chi minus. An important note, as you might expect, for eigenfunctions that should be obeying the maximality condition, chi plus and chi minus are orthogonal. And the matrix SZ is represented as chi plus SZ chi plus chi plus SZ chi minus chi minus SZ chi plus, and the minus minus along the second row, second column. Okay, and an example of the first row, second column is this matrix is basically written out 1, 0 times 0, 1 is equal to 0. And that's plus corresponding to 1, 0, minus corresponding to 0, 1. With the SZ, also wrote Z, SZ acting on it. Okay. Alright, so that's the matrix, and essentially examples of another example of the entries in the matrix is chi plus SZ chi plus is equal to chi plus h bar over 2 chi plus, and that's equal to chi plus goes to 1, 0, and for the row vector and the column vector, in the end you end up with h bar over 2. So that's how you calculate that. And if you continue doing these calculations, in the end you end up with SZ matrix being equal to h bar over 2 times 1, 0, 0 minus 1. Okay? And also, with no proof, S squared, what this tell you is x sub x squared times plus s sub y squared plus s sub z squared. And this evaluates to 3/4 h bar squared 1001. So we can consider something like S of x and then determine eigenstates Let's turn to class 4 to explore that. When you return, let's remark some more properties of our operators S. The following is S squared acting on the eigenvectors S chi S m sub S gives you S times S plus 1 h bar squared times S m sub S. Notice the subscripts here are a little bit like the YLMs. They refer to common numbers. And S sub z acting on chi S of S gives you quantum numbers m sub S, eigenvalues m sub S h bar, on the right hand side m sub S h bar times chi S m sub S. This is essentially all you need to know for, much of what you need to know for to expend, and a lot of it was a little bit hand-wavy, but you'll be studying some more details of how certain things are derived in your future courses. But that's beyond the scope of this course. Have a great day, and looking forward to seeing you in class. Bye-bye.